All right, so Newton's law of cooling says the rate of change of temperature of either a hot object or a cold object is going to be proportional to the difference of the object's temperature and the ambient temperature T naught. Okay, so what are we trying to measure here? Let's think about our variables. We have T of T, which is going to be the temperature of our object. And we have time. And for constants, we have the ambient temperature or the room temperature. And we're going to be just assuming that that we have a constant ambient temperature. Okay. We could always modify our model to change some of these assumptions, but that's what we're going to start with. Let's see. We're also going to have a proportionality constant. Let's call it K, which is going to be greater than 0. Okay. So this is coming from knowing that the rate of change of temperature is proportional to the difference of the object's temperature and the ambient temperature T naught. Okay, so we just want a proportionality constant to capture that. Okay, so let's try and capture this. So it says the rate of change of temperature. So this is going to be dt, dt, d capital T, d little t, is supposed to be proportional to the difference of the object's temperature and the ambient temperature T naught. So we're looking at the difference between the temperature of the object and the ambient temperature. And we're supposed to be proportional to this. So we're going to have some proportionality constant K. And I want you to think for a moment. Are we going to leave it like this, or will we want a negative sign? So if our object is hotter than the ambient temperature, will the rate of change of our object be positive or negative? Pause for a moment and think. If our object is hotter than the ambient temperature, we expect that it's going to cool down over time. If we started with, so we expect to see cooling. Okay. And when we have cooling, what we're going to have is that the temperature of our object is decreasing. So we want a negative derivative here. Okay. Let's also think this through in terms of a cooler object, just to make sure it makes sense. So if T is less than the ambient temperature, we expect the object to increase in temperature. We're going to see heating of the object. Okay, and so what we want to make sure is that dt is going to be positive. Okay, so in the first case, when our temperature was bigger than the ambient temperature, then putting negative K out front means that we're going to see a negative derivative. So we're going to be cooling. In the case where the object's temperature is less than T naught, then this will be negative. And we're multiplying two negatives together, so we're going to see a positive rate of change. That means that we're going to be heating up, which is what we were hoping for. Okay. All right. And so we see that this is our differential equation. If we had started out with an initial temperature for our object, we could write down an initial value problem, which we could then try and solve. All righty. Okay. And this is going to have quite a similar picture to the velocity picture that we had seen in the drag example. Right? Here our equilibrium is going to be when the temperature of the object is actually equal to the ambient temperature. Okay. All right. Next up, we're going to talk about mixing problems.